So with the understanding that we're skipping over a lot of important material, I already mentioned your beautiful introduction of Dirac in our
Yeah,
introduction.
I want to go back and read that now. That was very flattering. I like that. I'd like to see what I said.
Look, it was quite nice. But so what was his theory of quantum electrodynamics? And of course, that's a huge question. But I think what's significant for us here is the role that fields play in the theory and how it maybe changes our view of particles.
Yeah. So this is part of like a real kind of lurching towards a new theory. So one of the things, just like how, right after Einstein introduced special relativity, there was this kind of elephant in the room, which was, okay, you solved these problems for electrodynamics, but you've done it by breaking gravity. It was very clear in the early 1930s, right? Once we have this kind of second revolution in quantum mechanics coming to its conclusion, that, okay, great, you've got a new theory. It's really mathematically beautiful. We understand a whole lot about the quantum world that we didn't understand before, but it's flatly inconsistent with relativity theory. And so something needs to give. We either need to come up with a relativistic quantum mechanics, or we need to figure out some new way of solving the problems with electromagnetism, one that's compatible now with general relativity, which we have quite a bit of evidence for already, that is going to be compatible with the structure of space and time as understood in quantum mechanics. And so one of the first ways of doing this was proposed by Dirac. And Dirac's idea was that the kind of conflict between relativity and quantum mechanics had to do with the fundamental equation of quantum mechanics, basically the Schrödinger equation, being a sort of set in Newtonian spacetime, roughly speaking. It sort of presupposes a standard of simultaneity and not exactly a standard of rest, but definitely simultaneity, and so kind of a preferred state of motion from a relativistic point of view. And so Dirac's idea is, well, if we could introduce a modification of the Schrödinger equation that's compatible with relativity, then we'll have a quantum theory that ends up being compatible with relativity theory. And this isn't exactly how things turn out. The way in which we've come to understand Dirac's equation is not so much as an analog to the Schrödinger equation, but as a description of a new kind of entity, which itself has a quantum theory associated with it. And this new kind of entity is a quantum field. Okay, and so what a field is basically an entity that sort of extends throughout all of space, and can be described by assignments of different property values to different places. Classically, we can think of it as numbers associated with points in space and time. A quantum field is similar in some regards. It's similar in the sense that it's distributed throughout all of space and time. It undergoes dynamics that sort of locally depend on, so like what will happen a little bit later in one place is going to depend on how it's arranged nearby. And so it's not like, causally dependent on its distant regions typically. But it doesn't, these properties that we're talking about that, previously we could think of as numbers associated with points, have to have all of the quantum structure, right? And so the field values don't commute with one another. The field values in general can take discrete values for quantum fields. Many actually don't. You can have properties that don't take discrete values, but that's a possibility that needs to be accommodated by the theory. And so what Dirac's equation ends up doing is describing the almost pre-quantum dynamics of this new kind of entity that it turns out describes electrons very well, and describes quarks very well, describes the whole class of objects that we call fermions very well. I mean, his original understanding of what he was doing turned out to be kind of wrong, but the equation that he wrote down turned out to be extremely fruitful, and you eventually ended up with a theory of electrons, which is what he was trying to describe in the first place. That was in fact described by his equation. It just required some conceptual reconfiguring.
Well, now putting all of this together, how does quantum field theory relate to nothingness? I mean, through the void, and then I think the crucial idea here is the quantum vacuum state, and then the fluctuations that occur there.
Yeah. So the first thing to say is that when you reconceive of what kinds of properties things can have, like how things can be configured, you end up having a kind of a new theory of just like the modal space, like the ways in which physical stuff can be arranged. Now, we're now thinking, like, we say, okay, well, so that's the space of possible physical configurations. How would we think about one of those possible configurations as being one in which there isn't any stuff present? Like, is emptiness or is nothingness described as a physical state just like any other physical state by this theory, now that we have a new theory of what the physical states are? And the answer turns out to be yes. The way in which people have sort of come to think about this is by saying, well, once we think of matter as a distributed thing, the way that quantum fields force us to, we should be able to ask questions like, is the configuration of this quantum field one in which, if I were to perform an experiment to detect how many particle-like excitations there were in the world, I would be confident that there were none? Like, is there a possible state in which, were I to measure all of the particles in the world, I would definitely get the answer 0? And the answer is yes. This is the state that gets called the vacuum state. It's the lowest energy state in the theory. It's a state in which the theory predicts that globally there are no particles. And by there are no particles, what I mean is, there's a property in this space of possible properties described by quantum mechanics, which is the property, how many particles are there in the universe at a time? And that state is such that that property has the value 0. It's just like all of these other all of this other structure that we have in the theory ends up meaning that statement, which seems like a perfectly natural way of capturing the idea that you have empty space, does not have the consequences that you'd expect. Right? So one consequence you might expect is that if you're certain that there will be no particles globally, if you measure the entire universe at a time, that it will follow that there won't be any particles if you measure them locally. Like if you go in your backyard and you put a particle detector, will you find anything? And the answer is just like that consequence doesn't hold. It just doesn't follow from there being no particles globally that there are no particles locally. There can be particles locally. Now, I think the basic mathematical fact is what I've just described. Now the question is, like, how could we possibly conceive of a breakdown of such a simple and obvious inference? And the way that physicists do this, which is in some ways metaphorical, is to say, well, there's this kind of these like possibilities of little excitations, like it's like a roiling sea of stuff, and every so often something will pop up and then go back down. And somehow when we're talking about the global measurement, we're thinking about a kind of an average measurement over the whole universe. But somehow locally still, you can have these little excitations that could end up having consequences in certain kinds of measurements. Now, I mean, I should pause and say, like, you were asking these questions about like the weird modal structure of emptiness and relativity. You definitely get weird modal questions in this context, right? Because what we're asking about is what would be measured in empty space. But of course, in empty space, you don't have measuring instruments. If you did have measuring instruments, you wouldn't be in empty space any longer. And it's really unclear what we're talking about. Conceptually, the right way of thinking about it is you have these quantities, these things that we call observables. Those observables, in cases where we are making measurements, have an interpretation in terms of what the possible outcomes and the statistics for those possible outcomes and measurements would be. Here, what we're doing is saying, well, we can't actually perform those measurements, but we have a standard toolbox for talking about what the significance of certain states giving certain values for certain observables is. And so that's what's going on here. Like we're saying, like our local number operators, our local number observables will have non-zero expectation values in regions where, even though globally the number operator is in a state that is identically associated with zero particles. And the rest is kind of colorful metaphor, I'd say.
Well, Jim, the last thing I think will hopefully be a quick, maybe yes or no question before we say goodbye is, granted that quantum field theory and general relativity are two of our most successful theories. I think quantum field theory has been confirmed to something like 14 decimal points. Are you then of the opinion that going forward, any successor theory theory will leave no room for this perfect sort of void as we envision it with nothing in it? Because either way, I mean, like string theory, for instance, is fundamentally quantum mechanical, but we also know that general relativity, on the other hand, has this rich geometrical background to space. Is there any room for a very simple picture of a void, or is that just totally out?
Yeah, I think that's toast. I mean, it's ironic, but in string theory, you end up, in a lot of quantum gravity, actually, you end up thinking of gravity not as a force exactly, but as mediated by particles, the way that forces are mediated by particles. And so you have these gravitons that are kind of like photons. And so there is a possibility, I think, that we're going to end up wanting to say that some of these richly structured empty space-time solutions in general relativity should actually be thought of as sort of filled with gravitons, which are kind of like objects in the way that photons are kind of like objects. And so, it's plausible that some of the sort of rich conceptual structure of empty space is going to get left behind. But any view that looks like that, or any theory that looks like that, is going to be one in which you're going to have a gravitational vacuum like you have in quantum field theory, and you're going to have gravitons, spontaneously popping in and out of existence locally. And so locally, you're still going to have something that's going to end up looking like manifestations of curvature, even though globally, you're in flat space-time.